Good evening to one and all. This is the transformer basics about the transformer. World's first transformer patented in 1885. Electrical engineer Derry has designed this one. So coming to this one, transformer 125 years old. First transformer of the world is 1400 watts, 120 by 72 volts, 11.6 by 19.4 amperes in both primary and secondary, single phase shell type, core type made, iron wires, and so on. So how it has begun in 1831, Faraday's laws of electromagnetic discovered this. August 29, 1831, Sri Mitchell Faraday. 1864, 1885, and so on in 1910, considering the bushing wire developed. James Clerk Maxwell. So recognized the physics world in the greatest equations award. I think you know award. We have studied everything in our daily classes of electromagnetic field theory. So set of transformer and developments and achievements. So in 125 years old, born in 1885, we have seen already. First phase was first 85 years up to 1970, increase the power rating. And second phase, it is going for the design optimization. Third phase, reliability improvement. Coming to the large power rating of the 1920s, 15 MVA, and so on, 2002 onward, up to 2002, 1510 MVA, three phase 500 kV. So Mitsubishi has developed that one. Next, world's last three phase transformer, core type 1500, and shell type is 15 MVA up to 2002. So Indian scenario, 800 kV class and 420 kV class, and so on. We are having different manufacturers, Single BHL, Vedanta, Malaysia, like that one. 220 class, 400 MVA, 24 by 220 kV, 3H GSU and HVDC converter transformer up to 315 MVA, and 397 MVA one phase. And coming to the HV transformers, old scenario, 1930s 220 kV, 1950s 400 kV. From 17.1 to 2009, 1000 kVA, 1000 kV, 3000 MV line commenced in China. And growth of transmission line voltage in India, 1987 first transformer used in India, Idle Station, Darjeeling. In 2017, we are expecting we may commence 1200 kV. Already Vijay Electricals has developed this one, and it is in the transmission stage. Indian power system present, installed capacity is 148 gigawatts. Peak demand, this old details actually. Indian power systems 2025, and hydro 80 gigawatts, coal based 80 gigawatts, and growth of Indian capacity demand by 2025 is nothing but installed capacity is higher, and demand peak demand we are almost reaching internal capacity. In 2025 beyond, need to develop next level of transmission network, that is 1200 kV UHVAC network, main transmission line 1200 kV, and 400 kV AC system sub-transmission network, and so on. These are all different details. Distribution network also, minimum efficiency performance, transformers up to 200 kV, and 3-star labeled and financial grade of energy BE mandatory, and K-rated transformers in this one. So we are having different type of 3-core transformers, that is in 3-leg core, 5-leg core, and single phase transformers we are having 2-leg core and 3-leg core, 4-leg core. Like that one we are having different variations. So coming to the views in how the material is, metals and all those things in manufacture, there is the 3-core and all those things. Development in the core, reduction of core losses, merit joints, 2x2 blading, yokeless building. There are many more researchers are going. Insulation schematic, if you see this in insulations are also how it is going to be manufactured, and all the details are here. VPI dry type and cast wrist dry type. And core coil assembly, we can see the core coil, how the core coil is assembled, and it is going to be manufactured. SFC gas insulated transformers are also available nowadays, because the gas insulation levels, if we increase with the help of gas, the size of the transformer is also going to be decreased. So SFC gas insulated transformers, we can see the diagrammatical view of how the transformers for a higher level voltages. So gas cooled and gas insulated transformers, non-flammability, compactness, non-explosive, easy inspection and maintenance work, easy installation. So coming to the basics and how the electromagnetism in the transformer core. So if you see that one, they will explain how it is going to be connected. So current carrying conductor positive inwards and dot plus current going from U.
By convention, we represent objects going into and out of the plane using dots and crosses. Then imagine an arrow being fired from a bow. You can see the cross of the feathers of an arrow, it's travelling away from you. If you can see the point of the arrow, you've seen previously.
So we can see the current directions, how it is going to be for dot and star conventions.
Magnetic fields actually present this with field lines.
So the flux fields, flux currents and all of them. So this is the
now,
core
when we
area.
do this behind core, permeates just means
If you see the flux directions here,
iron can be
electromagnetic induction.
This is it's a
2 points in knowing this one. So I have taken this one from the YouTube
red
video.
arrows represent the magnitude of the current, so bigger arrows, bigger current. And I get
You can see the current direction. The current direction is moving from here like this one, like in the coil. The current is going outwards. The flux is moving like this one. And as the flux is there, whenever the current carrying conductor cuts the magnet, so whenever the conductor cuts the magnetic field, the EMF is induced this one. That is the Transfomer's law. You can see the
secondary coil.
see here.
So as long as once the magnetic field stays put field, which means we're always going to have a voltage induced on the secondary. Induced in the secondary will generate a larger voltage. It's on the primary, number of turns on the secondary.
So you can understand how the transformer is going to be. Voltage by secondary by primary, translated to the transformation K.
Divided by primary. If we take 10 turns on the primary,
So it is a 1:1 transformer.
we look at the ratio, secondary divided by primary, but it's 1. 10 divided by 10 is 1. Put that into the formula. What we know is that the output voltage on the secondary, those voltages are 10 volts out. 5 divided by 10 is 0.5. And the secondary, the output is a step down transformer.
So now I am moving to my basic animation based on the no load condition, how to draw a vector diagram and all those things. So if you see the diagram under no load vector diagram, there is nothing but the no load voltage, no load current, and flux phi m, maximum flux, that is nothing but phi m sin omega t. I have taken phi m as the maximum flux. So if you see the current, the flux moving because of this voltage profile, the flux is moving because of reluctance point of view. The flux moves in this direction, remaining will be the leakage flux, less amount of leakage flux will be there. So we have to understand the no load vector diagram, how to draw. As flux is constant, we are taking the reference as the flux phi, and because of the flux, magnetizing current I mu is developed, and IW, working component of current, because of the voltage V0, because of V0, IW is formed. So that is the induced EMF voltage E1, and we are drawing the vector diagram taking a parallel line of IMU and IW. So we'll get the I0, no load current, which is drawn from the supply mains under no load condition. An angle between V0 and I0 is nothing but the phi 0. Whenever we are applying a load, it draws a load current of I2, let it be, because it's a secondary point of view, I2 we are drawing. So from I0, initially when the load is switched on, automatically it has a opposite flux of phi 2. If you see the direction of phi m and phi 2, it is always in the opposite direction. Because of this one, the net flux will be phi m minus phi 2 or phi 2 minus phi m. So the flux will be decreased. But as per the concept, the flux should be remain constant. For that one, it draws an extra current of I2 dash from the supply mains, which will nullify this phi 2, extra phi 2, which is because of this I2. If you see the directions, the direction is opposite to this one, phi 2 dash and phi 2 are opposite, and phi 2 dash and phi m is nothing but the flux developed because of I0 and I2 dash. So the supply current I bar, I0 or I1 is equal to I0 bar plus I2 bar. So finally it cancels and finally flux remains constant, and here the current draws from the supply mains will be higher if the transformation ratio is equal, then I2 is equal to I2 dash. But here the transform coils, the voltage per turn coil is same, and here the turns are less and turns are more, then there is a difference. That's why we have taken as I2 dash. Right, we are drawing a vector diagram under resistive load. Resistive load means it's in phase. So we are taking V1, and these are all already we have learned about this one, I0 and Phi0 in the previous diagrams. Now here E1. Now we are drawing I2 because of the induced voltage I2, and similarly we are getting equal amount of I2 dash. And here we are taking a parallel line of I2 dash and parallel line of I0 plus I2 dash, that is nothing but vector addition. That's why we are getting a current of I1 from the supply mains and here the phi 1 is nothing but the phase angle between V1 and I1. V1 is nothing but the applied voltage under loaded condition, right? Now this is under inductor load. I have not done the manufacturing in this one. Animation point of view, this is nothing but the leakage flux, how it is going to be transferred. This is the flux because of reluctance path, which is having low reluctance path, the flux is moving, and the remaining flux is going to be higher. So this part, with this one, I thank you all for listening this patiently. And this is nothing but the basic of transformer and construction and transformer of working of transformer no load and loaded condition and its methodologies. Thank you one and all.